so here's the picture for an integral going from negative infinity to positive infinity. Basically, we're integrating over the entire real number line. All right, that's our interval of integration. And there's a little typo here that there should be, this one should be a plus infinity, not a negative infinity. So, and well, whenever we evaluate an integral with both limits being infinite, negative infinity and positive infinity, it's convenient to split the problem into two separate integrals. Well, in this case, I split the problem from a to 0 and then from 0 to b. But I mean, it could be a different value. I'm going to make a distinction when do we make those changes. I'll show you later. And as usual, the improper integral is said to be convergent if the limit exists. That is, our final answer, it's a finite value. But otherwise, if final answer is infinite, it's infinity rather, well, the integral is said to diverge. All right? So let's look at one example. So number one, we have the integral from negative infinity to positive infinity of 1 over 1 plus x squared. And we have looked at this integral a few times before. So any ideas on which rule do you think it fits? The arctangent rule. First of all, let's write it as a limit problem. So I'm going to split it into two limit problems. Number one, limit a approaches negative infinity from a to 0, and on the other hand, plus the limit as b approaches positive infinity, and in this case from 0 to b. Well, in this case we can just go directly to the arctan. No, in this case there's really no need to show the u du, because, well, what's u? That's okay, that's x. The derivative of x is 1. Do we really need to show that? Well, for something this simple, it's fine. Okay, so let's go ahead and limit b approaches, or rather a approaches negative infinity arctan of x from a to 0. Okay, well, technically there's an x over 8, x over 1. We don't really need to write down x over 1. Over here, 1 over a, but a is 1, 1 over 1. We really don't need to write that. Plus limit b approaches infinity, and that's also arctan x from 0 to b. Well, so let's set this limit. Let's evaluate. So that's the limit. A approaches negative infinity, and in this case that's arctan of 0 minus arctan of a plus limit of arctan of b minus arctan 0, and b approaches infinity. Okay, let's compute this limit. So in this case, well, arctan of 0, 0. All right, 0, 0. Okay, and then, okay, let's talk about arctan of a and b. So we are evaluating this we are looking at the behavior of the arctan function as x is going to infinity. What is that value? Pi over 2, I hear pi over 2, and this is the reason why we started the semester with looking at inverse trigonometric functions, and more in particular as well as the precalculus that involves, so recall that the tangent function looks like this. But of course we only took one portion of the graph in a way that the function is invertible, because this function right here doesn't pass the horizontal line, therefore it's not one-to-one, and finally it's not invertible. So we need to just take one portion of the graph, that is, I'm going to take only this portion, and these two vertical asymptotes right here. Number one is negative pi over 2 to pi over 2. So that's y equals tangent x. However, the inverse function, which is, draw the graph. We already got the graph for that one. It looked like this, with these horizontal asymptotes. Those horizontal asymptotes are exactly at the places where the vertical asymptotes came from when inverting this function. So also from negative pi over 2 to pi over 2. So when arctangent goes to negative infinity, the limit is in this case negative pi over 2, but on the other hand goes to pi over 2. So let's write down the result, but be careful with the signs, because what we got here, so we got 0 minus negative pi over 2 plus pi over 2 minus 0. Well, smile rule, that becomes positive. Pi over 2 plus pi over 2, what's that? Pi. That means the integral converges. All right, the integral converges. Okay, let's look at the next topic, the type 2 improper integrals. These type of integrals where, well, the limits in this case are not infinite. However, the limits of integration for which we are evaluating this integral go, or rather contain either a discontinuity in between the interval that we're integrating, or either one or both endpoints are actual discontinuity. So we'll have a look at one case of each. So let's set up this integral from 1 to 4 of dx over x minus 1. Well, number one, it's important to consider that there is a vertical asymptote for the graph of this function is, well, discontinuous at x equals to 1. What happens? Why? Because if you plug in 1, well, you're going to get 1 over the square root of 1 minus 1. You're going to get a 0 in the denominator. So we have a discontinuity at 1. And this one happens to be at the same time the lower limit of integration. So this falls in the category of an improper integral. Therefore, we will have to set this as a limit problem. All right, so let's see. So this will be the limit of the integral from a to 4 as a approaches 1. But in this case, we need to be careful. We need to be very, very specific with the notation, because this limit is being approached to 1 from the right. Can we approach a radical function from the left? Why? There's no graph, right? If you consider the radical function, looks sort of like this, you know? You can only approach from the right, but there's nothing coming from the left. So in this case, it's important to specify that one from the right. Okay, so that's the square root of x plus minus 1. And well, so how about we do a u substitution? Why not? So u equals x minus 1 du equals dx. And well, I'm not going to change the limits this time. We could, but I'm not going to do it. I'd rather go with the original limits this time. So this will be limit as a approaches 1 from the right, and that's the integral from, well, I'm not going to write the limits. That's the square root of u in the denominator and du in the numerator, and that's the integral u to the negative 1/2 du. And to integrate this, add 1 to the exponent, divide by that new exponent we obtain. In this case, negative 1/2 plus 1. It's going to be a positive 1/2. So that's limit. In this case, a approaches 1 from the right. That's u to the 1/2 over 1/2. Evaluate, or not yet, evaluation. And let me simplify this. So number 1, I'm going to rewrite this 1/2. Dividing by 1/2 is the same as multiplying by 2. Limit a approaches 1 from the right, and this u to the 1/2 is the same as saying the square root, but we can also back substitute for the quantity u, which in this case is x minus 1, and evaluate from a to 4. So let's see. We'll continue over here. So that's a 2 limit a approaching 1 from the right. So that's the square root of 4 minus 1 minus the square root of a minus 1. Alright, okay, so the square root of 4 minus 1, that's going to be the square root of 3. So that's 2 times the square root of 3. And well, where is this limit going to go when the radical is approaching 1 from the right for this quantity? In this case, a minus 1, 0. This one is fine because we're approaching from the right, so the limit will exist. And that's the square root of 1, which is 1. And, oh, not 1, it's 0 rather. Yep. And this is simply 2 root of 3. Because we got a finite number, whether this is an integer, a fraction, a decimal, an irrational, I, P, oh no, not I, actually E, no, and not imaginary. So this means converges. So integral. All right. Perfect, okay. Let's look at letter B. For letter B, we have the integral from 0 to 5 of dx over x minus 3. We need to be very careful with this kind of integrals because this integral, this integral doesn't look like anything special. At first glance, we can just do ln of x minus 3 from 0 to 5, and well, that's ln of 5 minus 3 minus ln of negative 3, which is absolute value. This is ln of 2 minus ln of 3, which is ln of 2/3. It seems like this is at first glance, right? However, the issue with this kind of integrals is because the limits of integration contain the vertical asymptote for this graph. And well, it's important to draw the graph. For this, let's go ahead and do the graph. So that's 1 over x minus 3. That's the reciprocal graph shifted 3 units to the right. That's 1, 2, 3. And this, yes, it looks like this. All right. And we're integrating between 0, yes, between 0 and 5, so the discontinuity will be contained within the limit. So that's why we need to split this integral into 2 separate integrals. All right. So This one is not the case in which one of the limits was a discontinuity. In this case, the discontinuity is in between. So we need to split this into two, and we will split the integral between 0 and 3. That is correct. Limit, and in this case, this is and let me call this C, because in this case this is not an A and a B, because these are not precisely two different values. We're splitting them, centering at a one single value. Let me just call it C equals to 3, C approaching 3, the integral from 0 to C.
Would it be from the left side?
And in this case would be from the left side. That is correct. And C approaching, you know what, in that case never mind. 3 from the right, and that's 1 over our dx. That's C to 5. Well, we already know the answers to these integrals. Well, in this case, let's label them integral 1 and 2. Let's do one at a time and see what happens. So let me do the integral 1, which will be the same ln, or rather limit first, ln of x minus 3 from 0 to c. Okay, as usual, upper limit minus lower limit. This will be limit c approaches 3 from the left, ln of c minus 3, absolute value of c minus 3 minus ln of absolute value of 0 minus 3. Okay, let's see what happens here when ln of 3 minus 3. Essentially, this would be this is where the trick, it gets a little bit tricky here. Okay, so here we're gonna get C3 minus 3. That's basically ln of 0, isn't it? But what's ln of 0? 1.
So you go to the right for possible.
Let's look at the graph of ln. How about that? So looks like this. It has an x-intercept at 1, 0, and well, as we approach 0 from the right, where is this graph going to? Negative infinity. So in this case, this is negative infinity minus ln of 3. Well, that doesn't matter. That ln of 3 is not going to do anything, really. So this is negative infinity. But in this case, because that first integral it's already blowing up to infinity, we don't have to bother and look at the second integral. Even if we get a finite value for the second integral right here, it doesn't matter, because we already got a negative infinity plus or minus even a tiny quantity or a big quantity. It's not gonna change this infinity value. So in this case, the integral diverges. All right, the integral diverges. Okay, so let's see what's next. Questions about any of this? Okay, so the p integrals. So these integrals are some, yes.
For that last example, so if that problem comes up on a test and we just do the first set,
that's fine.
We have to write integral diverges because
at least one of those diverge. So
do we have to write a statement, or we just write it?
Yeah, just integral diverges. So the minute one of the 2 or 3 or 4, well, maybe not that many, the minute one of the 2 diverges, that's enough. All right. Let's see the p integral. So this will be very useful for the upcoming chapter in infinite sequences and series. And this theorem right here is useful to determine the convergence or divergence of an integral of this form. Recall, yesterday when we started working with this topic, we were working on integrals. 1 over x cubed, 1 over the square root of x, cube root of x, but in this case, this theorem right here, or this definition here, is used to determine the convergence or divergence by just looking at the integral. Well, maybe doing some algebraic step, like very, very tiny step. The thing is that we need to observe these integrals. We're going to observe the power of the variable in the denominator of the integrand, and if that power is greater than 1, well, the integral converges. But otherwise, if the power is less than or exactly 1, well, the integral diverges. So let's have a look at these ones right here. Okay, so we have a few integrals. Well, observing this integral, the limits of integration don't really matter. So we can observe that p equals to 7. Well, is 7 greater than 1 or less than or equal 1? Converges or diverges? Converges. That's all. Let's look at the next integral. Well, we need to rewrite it first. From 1 to infinity, that's x to the 1/3 in the denominator. And well, let's observe the value of p. In this case, equals 1/3. Using the definition, will that integral converge or diverge? Diverges, right? Okay, let's do another one. The integral from 1 to infinity, x to the 5/4. In this case, p equals to 5/4. Converges or diverges? Converges. And last but not least, oh, look at this one. That's not in the form that it's required. Well, so this integral will diverge for a couple of reasons. I mean, look at the x cubed. X cubed is an increasing function. It's a polynomial function that gets bigger and bigger for positive values of x. And when you integrate it, you are even increasing the power of that function, making it a 4 power, right? So that infinity will be even more infinity than it actually was. That's one reason. The other reason is if we write the integral from 1 to infinity, x to the -3 in the denominator, p equals to -3, and because that number is less than or equal to 1, diverges. All right. And let's see, I think this is it for this section, isn't it?
Yeah.